All right, so we're going to get started. Today, it's my great pleasure to introduce Philip Liang. Philip is a professor at the Electrical and Information Engineering Department at the University of Sydney. He's also a visiting professor at Imperial College and a visiting professor at Harbin Institute of Technology, although I suppose the visiting professor assumes that you're not really coming back, but you go back quite a bit. And so today he's going to talk to us about, machine learning and FPGAs. So.
Okay, well, thank you very much for this opportunity to discuss our research. But before I do that, I'll just introduce my lab. My lab's called the Computer Engineering Laboratory, and we focus on using parallelism to solve demanding problems. So we're trying to find novel architectures, applications, and design techniques using VLSI technology, FPGA technology, and parallel computing. The application domains that we're mainly interested in include computer hardware, machine learning, and nanoscale interfaces. We've actually been working with some of our colleagues. So I'll just overview some of the other research that I'm not going to cover in this talk. Gecko challenge but basically it was to try to predict temperature and humidity. We took the first place in that one in 2013 and 2015. There's a CT scan annotation competition where basically you're given a set of CT images with associated annotations, and then you get given unseen images, and you have to try to annotate them as best as you can. We also took first place in that competition. These are like more conventional software-based applications. We've been working actually in collaboration with Microsoft Research into transistor matching at low temperatures for quantum applications. So what we're doing now is that we're measuring arrays of transistors in both conventional MOS technology and silicon germanium technology, and trying to understand their matching properties, and also trying to develop wide temperature range models for them. We've been working on time domain multiplexing of single photons. So this was, this is a photonic setup, and our contribution was basically to add, I joke, it's basically adding a few NAND gates to our contribution is, including a few NAND gates, but they're very important because in this experiment, what you do is that you detect single photons which are generated in pairs, and then you can, when you detect there's one photon, then you can multiplex the other photon so that it always appears on phase one of a four-phase clock, and then you can increase the probability that the photons occur on that particular phase. And that was in collaboration with a colleague in physics. We've been developing integrated graphene sensors, so using 2D materials which are very sensitive to small changes, and then developing all the associated analog circuitry that goes around them. And we're actually one of the groups that have a HARP system, which is the precursor to the Intel FPGA chip. And we've been working on that as well. So let me get to the talk for today. And that's on simultaneous learning and prediction in a kind of constrained environment. And I'll start by giving some motivation about why we would want to do this. And I'll actually talk about three different architectures that we've developed to do this. One is a vector processor. One is a pipelined implementation which achieves high throughput. And the third one is a braided implementation which achieves low latency. And then finally, I'll talk about some new work that we haven't published yet using random projections to do dimensionality reduction. Okay. So motivation. So we started doing this work because we were interested. We were working with a company called Exablaze, and Exablaze developed low latency equipment for low latency trading. And as I'm sure most of you know, in low latency trading, what they look to do is when new market data becomes available, to take advantage of a transient opportunity to make a favorable trade. The problem is that all the other traders in a co-located co-located exchange are doing the same thing. And what you want to do is you want to make an order before any of your competitors do. And so, you know, it's said that a millisecond reduction in latency translates to about $100 million a year for a large hedge fund. We also think that latency is important in other applications. For example, you could imagine if you could sense that you know, the events leading up to a blackout were happening, then you could perhaps take some action to prevent this before it's too late. And of course, latency is crucial in a situation like that. Also, machine prognostics, so it would be possible to monitor a machine and switch it off before, you know, it would really damage itself when something goes wrong. So Exablaze makes low latency, commercial low latency trading platforms. So this switch on the left there, that's a 48-port switch. So one thing that you want to do in a low latency application is you want to take your market data. You might want to make many copies of it for different machines to use. So their switch called the Exalink Fusion has 5 nanosecond fan out for that application. And if it operates as a layer 2 switch, it can do it in 110 nanoseconds. There are actually 2 companies that make this type of machine both based in Sydney. And that uses a large FPGA Xilinx Ultrascale. On the right here, there's the Exanic, which is a network interface controller, and it has, for 60-byte latency, it's only 780 nanoseconds. So we argue that the exchanges exist and the hardware exists. What's missing is that we're not able to do machine learning with the type of latency that we have here. Also in throughput, so our ability to acquire data is improving enormously, and with things like hyperspectral imaging and all that, we can actually generate data much faster than we can process it. There's another Australian company called Circa. They archive all of the Thomson Reuters financial data, and they have 3 petabytes of data in their database. It's actually strange. If you wanted data from the Chicago Stock Exchange and you buy it from Thomson Reuters, it will actually be served to you from Sydney. But they have 3 petabytes of data, but nobody's actually been through to try to learn anything from it because, you know, it's just not, it's just too much data. So, you know, there have been significant improvements in machine learning algorithms, obviously, but we argue what we can't do is that we can't learn at the types of data rates that we can generate the data. So we argue that EPIC technology is needed to, to deal with this. And EPIC is an abbreviation which I've used to summarize the advantages of FPGAs. So the E stands for low energy. which means that power doesn't become a constraint, or you can operate them off batteries, which is particularly important for satellite applications, which we're interested in the context of hyperspectral imaging. Parallelism, obviously, we can organize our computations spatially to achieve parallelism. Interface, so that we don't have to go off-chip in order to, which would add to the latency and decrease the throughput. And also it's customizable, so we can tailor the entire design to get the best efficiency. So, our work is using FPGAs to develop improved algorithms and system implementations for FPGAs. And I guess I don't have to tell you about, FPGAs, why we think the research is timely. Intel obviously are making a big play on FPGAs. In fact, one of the students from my lab, Duncan Moss, he's actually, he was playing with this early HARP system, and now he's an intern at Intel working on their machine learning libraries for this chip. Okay, so kernel methods. Who's familiar with kernel methods here? Okay, so not everyone. So linear techniques have been extensively studied. In fact, Gauss figured most of it out, many hundred years ago. And basically, a linear technique finds a solution of the form y equals wx plus b, where x is an input vector, and the w and b are the parameters to your model. Okay, so basically that describes a hyperplane in n-dimensional space. So there are different ways to get the w and the b, and the idea about regression or something like that is you're given a set of x's and y's, so a x vector, which could be all the features that you're training with in machine learning, and y is the desired output. You feed them to a linear regression subroutine, and it will come back with w and b for you, which you can then use in a model, because I can present a new x, and it will give me, an approximate what the model thinks y should be. So the advantages of this approach are it has a sound theoretical basis. It's computationally efficient. In fact, it could be argued computers are optimized for this problem exactly. The disadvantage is that you can only find linear type solutions. Now, there's one piece of mathematics which is really nice, and it helps us in our FPGA designs, and this is key to what we're doing. So while we're used to doing finding a model like this, we can express exactly the same model as a sum over, this is a subset of the training data. Okay, and this is called the dual form. So this is called the primal form, and this is called the dual form. And the reason we can do this is more intuitive if I show it to you geometrically. Say I've got all this training data, and I want to separate the red dots from the blue dots. Then I can find a dividing line, which, to which if this line, if it's less than that, it will be red, and if it's more than that, it will be blue. And I can do that by minimizing a function. This is a convex function. I can do this very efficiently. It turns out that I only need these ones which are right on the boundary in order to express this line. And so that's the primal and the dual form. In the dual form, the expression is just the sum, a weighted sum of these points there. And that's what that other equation was saying. If you're familiar with support vector machines, then these are called the support vectors. You don't need all the other information. Okay. Now, I said that one problem with linear methods is that if I'm given this problem, I cannot find a line which can separate the blue and the red dots. So the way that this is dealt with is that we can map it to a high-dimensional feature space. So we can take these points and we can map it to, say, 1 billion dimensions or something like that. In this high-dimensional space, then I can easily find a hyperplane which can divide these data. Now, obviously, the problem with projecting this into a high-dimensional space is that it would be computationally expensive. And so there's one other idea that we use in kernel methods called the kernel trick. So the kernel is a similarity function. You can think of it as comparing two vectors. And so if I have two vectors x and x prime, then actually the kernel function is defined in this way. You take this input and you project it to this high-dimensional space. You take this second input, you project that to the high-dimensional space, and then you take the dot product between them. Okay, that gives you a scalar value out. Now, if you choose a linear kernel where this is just the identity, then you just do dot product. You have all your linear techniques. If you choose a polynomial kernel, so you take this, you add 1 to it, which costs 1 operation, and then you raise it to the power of d, which just costs a handful of multiplications, then you are actually doing this. And this function, for the case of d equals 2, looks like this. So x1 squared, x2 squared, square root of x1, x2. And you can check that if you take the dot product of that, you get back what you expect. If you choose the Gaussian kernel or the radial basis function, then the kernel function looks like this, which is easy to evaluate. However, this mapping is actually infinite. So while it sounds strange, it's not that strange. It's an infinite sum, which when you sum it together, gives you that. So the main idea of kernel methods is that you modify linear techniques to kernel ones by replacing the dot products with this kernel function. Okay? And that actually does this mapping implicitly. You never have to directly evaluate it. You can express everything in terms of these kernel functions. And that's the kernel trick. So this is a support vector machine. We can actually train the model by, this is a support vector machine, and the decision boundary is given by this equation which I showed you at the start. And that's the primal form, and this is the dual form. So it's a sum over the support vectors. There are only 3 in this example, of this weight times the output I, each of these points, dot product with the input plus an offset. Okay? And the decision y would just be the sine function of this line. So if we do it this way, then this is a linear function. How do I turn it into a kernel version? Well, I take those x's and I project it to this high-dimensional space. And then, instead of doing this dot product, I do the dot product between these in the high-dimensional space. But I don't actually have to explicitly evaluate that. I just replace that by kappa xi x. Okay? And that's for training. I can actually do something similar for the learning part of the algorithm. Okay. For an FPGA implementation, that really helps you a lot because you don't have to worry about these data points. You just store these data points in memory. And so it becomes a very sparse, operations that you have to do here. So we never explicitly compute this. And just to give you an example, in the previous slide, I showed the example for d equals 2. If you choose d equals 6 and the input vectors of length 100, then this function gives you a vector of length 1.6 times 10 to the 9. Okay, now I'm going to go over quite quickly a number of different architectures that we've studied in order to try to implement these kernel functions. And we're trying to do this for different types of design criteria. So our first thinking was, okay, well, the operations that we need are basically matrix vector multiplications. So a vector processor should be pretty efficient. Okay. Now, one other thing is so we tried to design a vector processor, and the algorithms that we looked at are kernel least mean squares and kernel recursive least squares. So if you're familiar with adaptive filter theory, then it's a kernel version of the least mean squares and the recursive least squares filters. So traditionally, machine learning algorithms are batch-based. You store all of the data in memory, and then you call a linear solver or something like that. That will actually touch each of the data points multiple times and then find a solution. So it could be that if you're doing it in an online manner, not all of the data are available initially. And we argue that this type of technique is not suitable for really big data sets. The main architecture of the technique that we've been studying are that you take an input, each input one at a time. You make this approximation using a function similar to the ones that I was showing you earlier in the dual form. You make a prediction, and then you compare the prediction that you made with what the output should have been. From that, you can calculate the error, and then you modify your weights accordingly in order to improve the model. So you move in the direction of the gradient. So the advantages of this are that it's incremental. Hopefully you can do this with just an inexpensive state update when you get your new data. You only touch each data item once. And as we'll show, this can be done with high throughput and low latency. So the sliding window kernel recursive least squares algorithm looks something like this. Yeah. Sure.
So I'm trying to understand in the scenario you're talking about, where do you get the correct label data?
Where do I get the...
So you've got this yi coming in that tells you that's correct. So in the scenario you're looking at,
okay.
what's being
so
predicted?
Say we're doing, we're trying to learn a time series, then we'll get the next input, and then one cycle later we'll get the new output, right? And then I might be predicting whether stock is going up or down, say. And then I would know then what the output should have been, and then I can use that to...
Is it unsupervised learning or?
Well, this is supervised because I'm giving it the input and the output. Any other questions? No, good. So this is the sliding window kernel recursive least squares algorithm. We won't go into all the details, but suffice to say it's just it's a bunch of matrix vector multiplications. And for this particular algorithm, the computational complexity is about n squared.
Sorry.
Yep.
in the online learning versus the offline batch-based. So how do you prevent recent data from biasing your model?
So actually, for the financial data that we're dealing with, we are only interested in recent things. You know, we have a window of data and we can set the size of the window. And things which happened too long ago, we actually purposely wait to have, you know, smaller effect on what the output should be.
Does that potentially preclude you from finding better optima? I mean,
well, it depends on what you want to do.
the crash that you saw 10 years ago, right? And you see all the same patterns that led to it. And you're only looking at recent information, and you may be biased not to.
So actually, if you use, say, a recursive least squares algorithm, that gives you, you know, it's not as numerically stable, but that aside, it gives you exactly the same solution as solving the linear system. So in that sense, you can get the same answers. The caveat is that you can do that if you have enough memory to store all of the support vectors. So given that you've got enough memory to store the support vectors, then you're fine. But you know, in an embedded application, then maybe you don't have that, and then you'll have to throw some away. And then you can choose your strategy for how you throw away these support vectors. But in principle, if you've got enough memory, you can get exactly the same solution. I guess so, yes?
What's capital N? Capital N is the dimension
The-
of the data, or the number of
Yeah,
support
the
vectors?
dimension of the data.
Just the primal dimension.
So, you know, the dimension of the input. So, you know, a vector processor, I'm sure that everybody's familiar with it. Instead of doing a loop like this, we can have n copies of the ALU in the computing hardware. So we can do it in a single operation, and that gets us from, you know, n operations to a constant number of operations. So we implemented this as a custom vector processor using an FPGA. The instruction set that we selected is this one. So it's a simple vector processor, and the one thing that it makes it inefficient is that we need a lot of cycles, because there's a lot of latency in our floating point operations, to execute these instructions, and we can't actually overlap our instructions. In the Cray machines, they had vector chaining where they could do that, but you know, that led to inefficiency. This is what the data path looks like. Basically, we have n vector memories and n arithmetic logic units, and then we can do n things at the same time. This is what our results look like on a Stratix 5 with n equals 64. So in terms of power consumption, they're actually similar, they're comparable. However, we could achieve we could get the result in 1 microsecond versus, say, 16 microseconds for a 2.4 gigahertz CPU single core. And that gives us an advantage in energy, which is, you know, about 8 times. So this was done about 3 years ago, and we, you know, at the time we thought, well, all we need is a vector processor. But we got to thinking, well, actually.
So what kind of benchmark were you running?
So this is implementation of the kernel recursively squares algorithm. And we actually implemented the software one using a BLAS library. However, the vectors are not quite big enough to really, you know, take advantage of it.
So for the financial data, you mean?
So we actually tested it on conventional benchmarks like Mackie Glass. There are some benchmarks that people use to test this type of algorithm. Yeah.
Power, I'm a little confused. How can a CPU be consuming
13
less
watts.
half the power? of the
13 watts.
FPGA?
It's a laptop that we used, and 13 watts is
Yeah.
probably just the CPU, not the whole thing. But on the other hand, the FPGA was the whole board's power. So anyway, so we got to thinking. Actually, the system is not really using the ALUs too efficiently. You know, you need for the example of just multiply, you know, it takes 10 cycles of latency, so it's going to cost you 10 cycles to do a multiply. And, you know, even for things that we want to do like vector multiply, you know, if it's most of the time it's actually idle. It's not really utilizing the computing resources in an efficient manner. So that got us to thinking about HOS, high-level synthesis, so a C to hardware-based pipeline implementation. Now the difficulty with pipelining is as follows. If you get a new input, and you've got a heavily pipeline design, you have to propagate this input all the way to make a prediction. Then you have to wait till you get the output, which might not happen at exactly the same time. Then you have to calculate what the updated weights are, and only then can you process the next input, because the next input's going to use these new weights. So ideally, what you need, and the pipelines that we're talking about 200 cycles of latency from the input to the output. Okay. In our HOS-based implementations, we looked at this problem. Actually, it's the same as it's different. Well, kernel. So to put it technically, a kernel recursively squares algorithm uses like a Newton's method type approach to calculate the updated weights, whereas KNLMS, least mean squares, uses a stochastic gradient descent type method, which is less computationally expensive, but it doesn't converge as fast. So you can express it this way, in that the function that I want to find is the sum over the support vectors, and we assume that there are D support vectors, of this weight times the kernel function evaluated between your new input and existing dictionary entries. That's exactly equivalent to what I said earlier. So in this stochastic gradient descent style kernel regression, then given a new input, the way you calculate the weight update is that you evaluate this kernel function between your new input and each entry of the dictionary DI. And you make a kernel vector K, and then you actually see whether your new entry looks close to the closest existing dictionary entry. So if it's very close to a data point that you've seen before, then you just update the weights. If it looks very different to what you've seen before, then you'll add that data point to the dictionary. You'll make it a new support vector. And then you update the weights using this, which just takes a step in the direction of the gradient. Now, these types of algorithms always have parameters. And in our implementations, there are 4 parameters. So actually what we need to do, and as far as I'm aware, you know, in practice, all training algorithms or machine learning algorithms do this, you have to search over a number of hyperparameters, and then for each of the inputs, you pass the input to the model and you learn something. So with our pipelined implementation, we want to find some independent problems to process. And so our approach is to actually do the loop the other way. So for each of our inputs, we loop over the hyperparameters and then we learn the model. So this gives us hyperparameters number of independent problems that we can feed in our pipeline. And if we have L problems here, where L is the latency of our pipeline, by the time we've done this loop, then the updated weights will be available for us to process the next input. So that's what we did. We used HOS to generate a data path where we could feed the model, which consists of the dictionary, the weights, and here's the training example, and here are the hyperparameters. That will propagate through this 200-stage pipeline, and we will get an updated model here, we'll get our prediction here, and then we had some other logic to connect everything up together. We integrated it with Reefer on a PCIe board, and actually our initial implementations were not very efficient because we didn't get the interface right. The one thing that and then we went back and looked at the interface. The one thing that we learned was our original interface, we put the inputs in and then we got the outputs, and we would fill up a buffer with all the inputs. They would process, and then we'd get the output and we'd receive it, and then we'd fill up another buffer. It occurred to us about 6 months later that what we should have done is just do one big transfer of all of the data into the system and accumulate the error within the FPGA, and then we can just read back all of the errors in one go at the output and just select the hyperparameter setting that gave us the smallest error. And we didn't need to transfer in both directions. And that improved our throughput by a factor of 3. Anyway, this is what sorry. In other words, we did it stupid the first time.
I'm trying to understand what is the right way of doing it. So you have to record.
So all we need to know is which hyperparameter setting gave us the smallest error.
Okay, so you're doing the minimization of those in the FPGA.
So we can keep all that on the FPGA and just read out the final sum of all of the errors and choose the one. No, because we know the order of the parameters, so we can store all that on the FPGA, and then we can. Yeah.
Are there enough interesting hyperparameter combinations worth executing to keep your pipeline busy?
Yeah. So we, for example, we try 200 different hyperparameter settings, and we know which one each of, we know. Setting 1 is this, setting 2 is this, setting n is this setting. So we run it through all the data through the FPGA. We accumulate the sum of the errors for each of the hyperparameter settings. We store that in a memory. Then if we read the memory back, we can associate, we can find which entry in that table gave us the smallest error, and we know what setting that corresponds to.
Absent of FPGA, whatever I'm running on, what is the right number of hyperparameters I need to do the experiment effectively? Is that number 200? Is it 1,000? Is it 10? Right?
No. Well, it's problem dependent, and you don't actually know. So to put it a different way, when you're doing this optimization, you actually know the gradient, so you know the function, and you can calculate what the gradient is, and then you can do it. There are other parameters where you don't know what the gradient of the function is, and the only way you can work those out is by trial and error. You do a grid search or some kind of search over these hyperparameters. And that's normally outside of your machine learning loop. Does that answer your question?
Yeah, I mean, it's.
Machine learning doesn't have a good answer to that question. So the answer typically is the number of, if you're running on an HPC cluster, the number of nodes you have is the number of different parameters which I think you'll try. And it's a very, very active research area. The machine learning algorithms community hasn't come up with a very good answer yet.
So for example, one hyperparameter that we've been using recently.
This is a throughput problem, not a latency problem.
Yeah, this is a throughput optimized design. Yeah.
There's never a situation where I care about one experiment with one set of hyperparameters running fast.
Yeah, I'm going to talk about that
Okay.
in a moment. Yeah. But just to give you an idea, one of the hyperparameters that we're using in our hardware design is the word length. So by changing the word length, it's hard to understand the effect on the output, right? So all you can do is you try a bunch and choose the one that worked the best.
I had a question. So you're saying you put everything on the system, you let it do its thing, and then you get the errors, but you've lost the online learning aspects of it, correct? So now it's just a parameter tuning machine.
Yeah.
You can't stream live stock market data.
Exactly. Yeah. But I'm going to address that. And you can do a streaming if you have 200 independent things to do. So say you've got a different model for different stocks. Now I've got one for Microsoft and one for Google and whatever. Then I could run a different model on each of those, and then I could do it.
But wouldn't that go back to your thing that you said that you made the initial choice incorrectly? Because you were
No, sorry.
IO into the
So
system?
the initial choice was just in the system implementation, how I do I/O to the core. So just how I get data in and out of the FPGA. That made a factor of 3 difference in our throughput.
So there are these, like if you don't have enough experiments to run, have you looked at sort of the asynchronous sort of SGD methods? So
Okay, but you still have the problem that you need to calculate your new weights before you can.
Right, but that's I guess in distributed systems for deep learning, they use like parameter servers, and you have sort of worker replicas that take a copy of the model weights, which may be inconsistent with the other worker replicas, but then you have a merge function eventually. So you can create sort of independent work, but your convergence guarantees might be a little wonky.
Yeah. There are a whole bunch of heuristics that you can.
It seems like that method would apply pretty well with the pipeline here, where each pipeline instance would have a model replica. Like you take a snapshot of it, and at the end of the pipeline, there's a merge step where.
Yeah. Or another way you can do it is just don't worry about using the updated weights. Just use the old weights.
Just a stale.
Yeah, and that actually works quite well too. Okay, so here's an overview of the performance of this. So compared to the vector processor, which is this one, the vector processor is actually a lot easier to program because you can make a simulator and you can program it without redeveloping the hardware. But we made a core. It runs in single precision floating point. It can take a new input vector at 300 megahertz, and if we use our updated system implementation, that adds about 30% overhead to it. And compared to, say, a naive HOS synthesized implementation, that's about 2,000 times faster. And it was actually, surprisingly, 500 times faster than our vector implementation. So with this type of implementation, we could do machine learning. If we have 200 independent data streams, then the data rate that we're talking about is 70 gigabits, which is about as fast as you can send data to an FPGA. And it achieves 160 gigaflops. Yes?
Naive versus the hand tuned.
So naive is if you take the source code to our implementation in C and pass it through the tools, you get an implementation, and that's the kind of performance that you get.
The hand version is like
This is Vivado HOS.
But is that like 6 months of work? Is that what you're saying? The hand version. I'm just thinking.
So the hand version's about 6 to 12 months of work. Yeah.
Was the CPU? So what is the CPU?
The CPU is a single core implementation in software.
Was it executing the C code?
The same Xeon 2.4 gig
Because
i5.
I mean, the Xeons have probably per
No,
core,
not Xeon.
like a Haswell today would have about 70 gigaflops per core.
Uh-huh. Yeah, but
So
you can't
maybe-
sustain that for these small vectors that you're.
If it's in cache and it's using AVX2, I don't see why not.
Because you have to compute the kernel function and the weight updates. Yeah, so basically you're computing this. So you can achieve that for so you've got this you can only achieve that for the matrix well, you have this kernel function, right? So you take, it looks like this. So the main bottleneck is computing something like this, right? And you can't achieve anything like the full performance of the processor to do that.
That looks like a vector subtract.
So yeah, you do a vector subtract, then you
That's an inner product, right? So
then you compute the magnitude of that, so that's a sum of squares, yeah, and then division and exponentiation. Yeah. So while I agree, you can
But was it using AVX? I guess that's my question. Was it just using a straight line C compiler?
no. So we played with all of the so it was using AVX in the sense that the best that GCC could do, on that processor. But
You said you were using OpenBlast or some blast implementation, right?
well, we actually tried a whole bunch of different ones. OpenBlast was no faster. No, so Blaz was no faster than not using Blaz. Yeah, and then so basically we ended the one that we're comparing with was the best set of compile options that we could find with that. But I agree. One could probably do a better software implementation. But I don't think that you can be achieving this type of performance in software. So now I'll talk about a braided implementation. And actually, because these were 3 different pieces of work over 3 different students and we were exploring different algorithms and all that, we implemented a different algorithm called NORMA. NORMA, I would say, is almost the same as the previous implementation in that the algorithms of very similar style. And again, we're evaluating this function, and we're computing the gradient and taking a step in the direction. As with all of these, we could implement classification, regression, or novelty detection with slight changes to the algorithm. And if we're doing novelty detection, which is the example I'm going to use, then our update will be, so these are the weights, right? And the update is basically a decay of the weight. And so in novelty detection, what you try to do is you try to put all your data inside a ball of radius rho. And if the evaluation of this prediction is outside of this ball, then I want to add this point to the dictionary, okay? And then I would do this. If it's not outside the ball, then all I have to do is the weight update. So the actual the actual computation is actually the same, this dual form. Okay. So there are two cases, when I add something to the dictionary and when I don't add something to the dictionary. So our data path looks something like this. We have a new example. We have our kernel function evaluation hardware here. We have our dictionary in here. And so when we get a new input, in parallel, we compute all of these guys, and then we multiply by the weights, and then we reduce it by summing them to get our output. So in the case that we don't add something to the dictionary, this dictionary doesn't need to be updated. We still do this, we multiply by something different, and we produce the output like this. So NORMA is a sliding window algorithm. So if we add this new dictionary, then our dictionary goes from this to, we put this new data point in here, and we throw away the last data point. The weight update's just a decay. And the update cost is small compared to computing this function f. So remember what I said about the issue of the dependencies? Well, we wondered whether that's really true. And we got some inspiration from a carry select adder. So recall in a carry select adder, what we do is we want to minimize the latency from along the critical paths. So from the carry input to the output is the longest path. And the way we make this shorter is we say, okay, I don't know what it's going to be. I'll play both hands. And I'll assume that the input was 0, and I'll have the hardware for that. And I'll assume that the input was 1, and I'll have the hardware for that. And so the critical path is shorter. And when I know what my carry should be, I'll put that in here, and I'll select what the correct output should be. So remember, in our design, we have whether we add something to the dictionary or we don't add something to the dictionary. So I can actually have both cases evaluated in the data path, and then I can have a multiplexer here, and I'll basically choose which of those it should be. And that works perfectly if I have one pipeline stage. Right? If I have p pipeline stages, then I'm going to have to do this p times. And so that's why we call it braiding. You take your new term, your old term, you compute this partial sum, and you do it many times. So to generalize it to p cycles, the equation looks like this. It's a little bit messy, but it's manageable. And we can build a data path like this, and we can make our implementation. So this time we didn't use HOS. We actually implemented this in Chisel from Berkeley. And this is the input vector length. And we basically used not a huge FPGA, and we can fill the FPGA. The area is kind of like the dimensionality of the input vector times the dictionary size times the number of our word length squared. And I guess this is the punchline of the talk. If we compare, we're not comparing exactly the same thing, but if we compare implementations of KNLMS on the vector processor with pipelined implementation with this braided implementation, we also went from single precision floating point to a fixed point implementation. Then we have a drop in frequency because we've increased our critical path quite a bit. But we've been able to reduce the latency from 200 cycles down to 10 cycles. And our throughput is still 1, so we can still take a new input vector every cycle. So that brings our latency down to 89 nanoseconds, and our throughput is only. This is reduced by almost an order of magnitude, and we kind of increase the the throughput's reduced by much less, by about 2.5 times. Just one other thing that we haven't published yet, but we're quite excited about, and that's random projections. So there's the Johnson-Lindenstrauss lemma, and, well, maybe I should take a step back and say in machine learning, one common step is that you apply something like principal component analysis or something like that to reduce the dimensionality of your input data. And it turns out that you can do a pretty good job if you just multiply, you make a low rank approximation by multiplying by a sparse random projection matrix. So it's a matrix that has mostly zeros, and the non-zero entries are -1 and +1. And you can reduce dimensionality from M to K. And of course, if we're only multiplying by +1 and -1, we can make a very efficient FPGA implementation. And what we've seen is that if you integrate it with something like our braided implementation, then you can reduce the dimensionality with minimal change to the hardware, which allows you to either solve larger problems or to use less hardware to solve the same problem. So to conclude, we believe that systems of the future are going to need to use machine learning to interpret and process the data adaptively and in real time. So the implementations need to be energy efficient, low latency, and single chip. So I described a number of techniques to do simultaneous learning and prediction. If you want flexibility, the vector processor is good for that. You can implement almost any kernel method without needing to recompile the FPGA design. If you want to do it with high throughput, then you can use a pipelined implementation, and also presented a low latency braided implementation. And also presented the idea that you can use random projections to make really efficient implementations of dimensionality reduction. So if you think about latency versus throughput, then the vector processor will sit here. It's not brilliant latency or throughput, but it's good for design productivity. If you want low latency, then our braiding implementation gives you less than 100 nanoseconds of latency for small dictionary sizes. For pipelining, we have high throughput, and we can achieve more than 70 gigabits of bandwidth. So thank you very much.